Okay, welcome to Unit 2. It's a super short unit. It's basically an introduction to solutions and different types of reactions. So we're going to go through first. The first day is just, again, recalling some important information. Bless you. So looking at this first question, it's asking us to list whether the following substances, when they're in solution, they're going to be strong, weak, or non-electrolytes. First thing I want to do is talk about what an electrolyte is. So who can remember? Electrolyte. What does it mean to be an electrolyte? Just the word, the definition, electrolyte. It's a solution that what? I mean, that's the basis of it, but what does an electrolyte do? Why is that word electro in it? Okay, it electrifies you. It conducts electricity. That's a little more less dramatic than electrifying you. But yes, it has the potential to conduct electricity. What makes it have the potential to conduct electricity? What's floating around in an electrolyte? Not molecules. Ions. Ions. So when you drink Gatorade, the electrolytes in there are your potassium ions, your magnesium ions, or all those other salts that have dissolved into ions, okay? So I heard someone say salt. Salt is correct, but only if the salt is a soluble salt that dissolves. So these free ions make the solutions electrolytes. So let's talk about what makes up some of these electrolytes. If we have a strong electrolyte, we're assuming that the substance that we put in the solution breaks up 100%, okay? So what are the things that do this? Well, you have your soluble salts, which are your ionic substances. Tomorrow we're going to discuss what ionic substances actually do dissolve. Not all of them do. Well, all of them do a little bit. But in order to be a strong electrolyte, the majority of the substance has to dissolve. So your very soluble salts create strong electrolytes. What else dissolves 100% in water? See if anybody remembers. Not just salts. Just a different type of solution. Think back to nomenclature. What other stuff did we name? Acids. What kinds of acids? Not all acids will be strong electrolytes. Which ones? Hydrochloric. What describe that? I don't want specific acids. What category of acids dissolve 100%? Strong acids. Good. You're getting there. At least you're trying. First period sat there, and I felt like I was in the woods by myself. Strong acids and bases are defined as strong acids and bases because they 100% ionize. So those will be your strong electrolytic solutions. What about the weak ones? Weak solutions. You can kind of already tell, based on what I wrote here, what would make a weak electrolytic solution. These are solutions that have some ions floating around, but not a ton. Weak acids and bases, good. So if you have weak acids and bases, those will be part of your weak electrolytic solutions. Now, there are some ionic compounds. We're not going to worry about those today. You're not going to even worry about those until we get to solutions in Unit 12, a long time from now. But there are some salts that are barely soluble that will ionize a teeny bit, that do create a little bit of a electrolytic situation. But for now, the only weak electrolytes we're going to worry about are your weak acids and bases. All right, non-electrolytes. Let's see if you can get this. What are some things that we can dissolve that don't ionize but that still dissolve and make solutions? Any ideas? Think about your everyday life. Sand. Does sand dissolve in water? Good try, though. No. Okay, but at least you're thinking. Sugar. Sugar. Organic stuff doesn't always dissolve, but if we have organic substances that do dissolve, they will be non-electrolytes because they won't split into ions. Let's go back to sugar. What's the formula for, like, glucose? C6H12O6. How does that differ than anything I have listed so far? Go back to nomenclature. All nonmetals, covalent, okay? So your covalent substances or your all non-metals. Now, I'm not saying they're always going to dissolve, because not all of them do. Some of them, like some of the organics, are so nonpolar they're going to just kind of float and hang out. But if they do dissolve like sugar, sugar dissolves, but because it doesn't form ions, there's no way electricity can be passed to the solution. Okay? All right, in order to be successful with this, I want to review your acid-base rules. So I'm going to kind of draw, we don't need too much room over there. Let's talk about strong acids. Now I'm going to get specific because this is where y'all were trying to go. There are 3 strong binary acids. 3 of them. Anyone remember what they are? HCl, HBr, HI. What I say to remember that, I bring clay. That's it. I bring clay. Those are the 3 strong binary acids. HI, HBr, HCl. What about your ternary acids? There's a rule. Yes, 2 or more oxygens than hydrogens. 2 or more oxygens than hydrogens. 2 or more oxygens and hydrogens make the acid strong. So an example would be HNO3 versus HNO2. HNO3, does it have 2 or more, at least 2 or more O's and H's? Yes, so that makes this one strong. HNO2, does it have 2 or more O's and H's? No, so this one is not strong. Okay, these strong acids and bases will totally dissociate, making strong solutions. There is one rule that supersedes all of them. If you see an organic acid that has a ton of O's, a lot of you will be like, oh, that has way than 2 more O's and H's. If it contains carbon, it supersedes any other rule and is weak. Carbon containing acids are weak. All right? Okay, let's talk about bases. Bases usually are defined as substances that have what in them? Usually, not always. The hydroxide ion. And we're specifically talking about metal hydroxides. When we're looking at the metal hydroxides, your group 1 plus the bottom of group 2 being strontium and barium are strong bases. They're going to dissociate 100%. Calcium hydroxide, because it's kind of in the middle, it's accepted either way on the AP, depending upon how they define it. And I'll tell you this, but I don't want you to worry about it because they'll take it either way. But the true way they look at it is this. If that is a saturated solution versus a weak solution, meaning, by weak I mean, I shouldn't say weak, that'll throw you off. I'll say dilute. Thank you. So this, if they give you a molarity of like 0.1, here's the thing. Calcium hydroxide, if it's a dilute solution, there's enough room. I hate to use this. This is so like mundane the way I'm explaining it. But there's enough space for that lattice to break up and all the lattice to be in ions. So with these dilute solutions, all the calcium hydroxides will dissociate. Okay? So this would be considered strong, and we'd have a current. If it's supersaturated, you not only have, there's a bunch of solid falling out and not space for ions. These saturated ones are considered to be weak. All right, but I really don't want you to worry about it. I was just trying to tell you for informational purposes. All right, you can go either way with that. They will accept either. So any other metal hydroxide is going to be weak. The rest of group 2, all the transition metal hydroxides, those are all weak. Then there's one special little base, NH3. NH3, you might not recognize it as a base because it doesn't have a hydroxide in it, But what happens with this is when you mix it with water, it will react and form a hydroxide in solution. And I'm going to show you that when we get to this problem over here. But this is always considered to be a weak base. This is actually the most famous weak base that we're going to use in AP when we get to our acid-base chapters, our Unit 11. So you just need to know it's a weak base. This is usually a gas. Does anyone know what this is? It's ammonia. When you buy it at the grocery store, it's in liquid form, right? You know what I'm talking about? I'm noticing that not a lot of people at Westlake are buying ammonia. I was asking students, have you ever smelled ammonia? It's really, really odoriferous. What it is, the gas is bubbled into water, and what you're actually buying is ammonium hydroxide. When you open it, think about the lab we did. What happened when you shook the Coke? The gas left, right? Well, this is pretty much what's going on when you buy the ammonia. That's why it smells so bad. When you open it, that gas is leaving. Okay? Let's go ahead and work these problems now. And I'm going to put this little guy. I'll put him here. Okay, starting up here, you have to list whether these are strong, weak, or non-electrolytes. And then if it is strong, we're going to write the dissociation equation. We're actually going to write for weak as well. 8ClO4. Classify. What kind of compound is that? Come on, guys. What is HClO4? Strong acid. Strong acids make it what? What does that make this? Strong, weak, or non-electrolyte? It makes it a strong electrolyte. Okay. When we have a strong acid, it 100% dissociates. So my arrow is a single arrow going in one direction. And it dissociates into what two ions? H plus what? ClO4 minus. Okay, C6H12. Strong or weak? Or what? What kind of electrolyte is that? It's a non-electrolyte. Why? It's a covalent substance. Not to mention, this is actually the substance that it's an organic substance that is just not going to dissolve. It's actually going to kind of just float. So this does not dissolve in water. Doesn't even dissolve. All right, I'll write in water. Okay, lithium hydroxide, what's that? Strong base, good. Totally dissociates 100%, one-headed arrow, makes lithium ion and hydroxide ion. What kind of electrolyte is this? Strong electrolyte. Okay, this one's going to kind of be an exception. I know it said if it's strong, write an equation, but we can write equations. We're not stupid. We can do this. Ammonia is what? A weak base. So this is a weak base, making it a weak electrolyte. So it is going to create ions in solution that can conduct electricity, but not very many of them. So remember I told you that this doesn't, you don't get OH off of this directly. We have to mix it with water. Bases are proton acceptors. So an H is going to move. And I have this equilibrium arrow here because this doesn't happen 100%. Only some of the ammonia reacts a little bit with some of the water, and we go back and forth, with equilibrium being favored on this side. We have more NH3 than we do ions. What do we make, though, when we do that proton transfer? Just move an H. NH4 plus OH minus. You're right, it is NH4OH, but that is soluble, and that's going to be in ions. So it's the OH we produce there that makes ammonia a base. This double-headed arrow is indicating it's a weak system. That's why it's a weak electrolyte. Okay, moving on to CaCl2. What type of compound is this? An ionic compound. I will tell you tomorrow you're going to go over the rules. This is a soluble salt. Since it's a soluble salt, it will dissociate, making this what type of electrolyte? Strong electrolyte. So what will it dissociate into? What ions? Okay, we have 2 Cl minuses. Good. Okay, last but not least, what is our last substance? Acetic acid. What is that? It's a weak acid making this a weak electrolyte. Since it's weak, it doesn't dissociate 100%, so I'm going to have my double-headed arrows. A few of them will dissociate. A few of these ions will split up, and what will a few of these acetic acid molecules will dissociate to make what 2 ions? H plus plus. But it's weak. That's why we have the double-headed arrow. Okay? Any questions on that? I'm going to pause this. Okay, let's move to some molarity work. Now, some of you, depending upon what teacher you had, might do molarity via dimensional analysis, which is fine. I really don't care how you do it. I'm going to show formula because that's what I'm most comfortable with. But what is the formula for molarity? Molarity is a unit of concentration. Molarity is equal to what? Okay, we're going to take it a little further. Moles of what per liter of what? Moles of? What's the step that we dissolve in a solution? Solute over liters of, nope, not liters of solvent, liters of the whole thing. Liters of solution. Good. Now, in Chem 1, it was acceptable. I'm not saying it's not acceptable, but I really want you to look more adult in your work. The capital M was like, you'd write, this was 5 capital M. Yeah. Is capital M a unit? No. What are the units of molarity? Moles per liter. So this is what I want to start you seeing right after your molarities. Something's 5 molar, you write 5 moles per liter. The reason this is going to be helpful when we get into some more advanced problems, you're going to need those units there to start canceling. You're not going to have a capital M to cancel anywhere, and you'll be like, where's the canceling? So write units of moles per liter. So we're supposed to solve now for 0.875 moles in 1 liter, in 500 mils, in 100 mils, and then in 6 liters. This is going to be pretty easy because they give us moles of NaCl. So what are we going to do? We're going to say molarity is equal to how many moles? 0.875 over 1 liter. Ooh, that's hard. What's the molarity here? 0.875. And I'm not ignoring sig figs. I'm basically ignoring the volume, the sig figs on the volume. Let's just do 3. Forget that. I don't like 1 sig fig things. Yes, Johnny? This is an assumption at this part. You are correct, and I'm going to address that very thing in the next problem and pull out some volumetrics and show you the difference. So Johnny was saying, I thought you had to have liters of solution. A better problem would have been for this problem to say in a liter of, a total liter, 1 liter solution or something like that. All right, the next one. Molarity is 0.875 over, what do I put here? 0.5. So what is my molarity? I need calculators, folks. I'm going to pause this till you get your calculators out. Come on. 1.75 moles per liter. All right, 100 mils molarity is equal to 0.875 over, this is 0.1 liter. So dividing by 0.1 gives us 8.75 moles per liter. And our last one, 0.875 moles divided by 6 liters equals 0.146 moles per liter. Does it make sense that our concentration is dropping the bigger the volume we use? Yeah, mathematically, obviously, but does it make sense mentally? If you have a set number of moles, you dissolve it in a small volume, it's going to be pretty concentrated. That same moles you dissolve in a much bigger volume, it's going to be much less concentrated. And you can see that with the 0.1 liter and the 6 liter, right? Okay, let's move on to the next problem where you're actually going to learn about making solutions. Eventually, in the lab, you guys are going to be making your own solutions. And it's an important skill. You might be doing research in the summer with under a professor, or you might just be getting a job as a lab tech somewhere to help pay for some college or something. You never know. So I do want you to know how to make a solution. Here it says, how would you prepare 500 mils of 0.05 molar of copper 2 nitrate? Now, it's not saying much about the copper 2 nitrate, so we're going to have to assume they're saying that this is a solid. Again, a better problem would have been to say solid copper 2 nitrate, but we're assuming I walked into my stockroom, I pulled off copper 2 nitrate solid off the shelf, and I'm like, okay, Lincoln, here you go, make the solution. So what are we going to do? Any ideas? First step. Find the molar mass. Okay, well, let's back up just a smidge. We all know molarity is what? In this case, moles of what? We need moles of Cu1032 over liters of solution. What do we know? How would you prepare 500 mils? What is that? 0.5 liters, but where does it go in our formula? Isn't that our liters of solution? Right. So to find the molarity, we know the molarity, we need to make a 0.05 molar here. So your job is to know how much copper 2 nitrate to put into that total liter of that many liters of solution. So what do we have to do? Solve for moles, and then what? Find the mass. Why are we finding the mass? Why can't I just know how many moles to put in there? Winborn? No. Okay, go. Someone said it. Was that Madison or Maddie, one of y'all? What'd you say? That's exactly what I wanted her to, what I was going at. We can't just solve for moles and go, oh, I'm going to put X number of moles in this flask. I don't have a mole scale, right? I really wish I could invent one where I could just like speak to it and tell it the compound and then weigh it in moles. But yeah, it doesn't exist. So we're going to have to measure out in grams. All right. So what we're going to do, I bet you Siri could do it. Did you say that what you said? I was thinking about that. That would be cool. Siri, weigh out, but we need an actual scale. It needs to be a Siri scale. I'm so in on that. I'm Pat. This is recorded. It is September 13th at 10:03 a.m. This is my and Noah's idea. Nobody take it. It is patented and done. Siri scale for chemists. Okay, so let's go ahead first and solve for moles. So 0.05 is equal to moles divided by the 0.5 liters. So 0.5 times 0.05 gives us how many moles? 0.025 moles. And that's moles of what again? Cu copper 2 nitrate, cupric nitrate. But to make it a useful number, I need to convert it to grams. So I've got for every 1 mole, what's my molar mass? 0.5 what? 57 grams. Okay, rounding to 3, let's just stay with 366. What is my number of grams? 4.69 grams of copper 2 nitrate. Okay, who thinks they know how to make the solution now? I'm actually trying to trap you, but don't be scared. Who wants to try it? What would you do? How would you explain how to make this solution now? Because this would not be enough on a test. Cough, cough. If I were to ask you how to make a solution, I want you to figure out mathematically what you need, but then you got to explain how you do it. Who wants to try? You would take what and do what? Johnny, go ahead. Okay, that's for gases. So no, it's not hard. All we're going to do, I'll start you off. We're going to take 4.69 grams of copper 2 nitrate and do what? Put it in 500 mils?
Oh, no.
Okay. Noah's thinking. We're not going to subtract. Okay, here's the thing. We need our total solution to be 500 mils. If we have the solid in there, it takes up a little room, right? So we can't just add 500 mils to it because then our solution total will be, how much room does it take up? We don't know. There is no subtraction. You cannot subtract the solid, right? Laura? Add it until you do what? Until you get to 500 mils. So let me explain that. That was perfect. Here I've got some volumetric flasks I'm going to show you. These flasks have lines on them that have a predetermined volume. This happens to be a 500 mil volumetric. We're making 500 mils of solution. There's a line here. So to make the solution, we would take 4.69 grams of the copper 2 nitrate, put it in here, and then fill it to the 500 mil mark. That takes care of everything. We have 500 mils of solution, and we have the proper number of moles in that 500 mils. So that's what you say. Jot it down. This is what I expect. Take 4.69 grams of CuNO3 and put it in a 500 mil flask. Fill to the 500 mil mark with what? With water. Okay, and that's what your answer is. This is what I'm going to be looking for. Okay. Another fancy way to say fill to the line, you can say I'm going to QS it. What QS means? Well, there's a Latin word for it, and y'all can look it up because I don't remember, but it basically in English, quantity sufficient. So when you say you're QSing, it means you're filling to the line on the flask, because these only measure one volume. Okay, and we use these flasks because they're more accurate than a graduated cylinder. Okay, they're also way more expensive. All right, you ready to try another one? Okay, this is one type of problem that you need to know. And the other one, calculate the volume of a 0.5 molar copper 2 nitrate solution needed to prepare 250 mils of a 0.4 molar copper 2 nitrate. How is this different than the last problem? Perfect. You said the word I was looking for. You're diluting a solution to make another solution. You're starting with a liquid, and it's got its own molarity already, and you're physically diluting it. And that was what I wanted to hear, was that word. We're making a dilution problem here. Does anybody remember the dilution formula? It's simple. It's repetitive. It's got an M in it, and it's got a V in it. Philip? Close, not plus. Times. Molarity times volume equals molarity times volume. M1V1 equals M2V2. And that's what we're going to use to figure out how many mils of the concentrated stuff we need to make our new solution. So I'm just going to kind of read and fill in as I go along. Calculate the volume, that's what I'm looking for, of 0.5 molar copper 2 nitrate needed to prepare 250 mils. What do I write down? Okay, I'm going to play devil's advocate and say I can do this, and I'm okay with that. Does anybody know why that's okay here? It'll give you your volume milliliters. Why? This is a proportion. This is to this as this is to this. We're not canceling out units here at all, okay? So feel free. If you just want to say, hey, I'm always going to convert to liters, go for it. That's okay if you want to put 0.25 in here. But whatever you put in here, you're going to get out here. Why do I prefer mils? You'll see, when you see the answer, you'll see why I prefer mils. And then what's the molarity of our stock solution? This is called a stock solution. This is what we're doing the dilution from. 0.04. I'm sorry, that's not the stock solution. My bad. This is what we're going to. Our stock solution is the more concentrated one. All right, so we want 250 mils of a 0.04, and we're starting with 0.5. How much of that 0.5 do we need? 20.0 mils. Had you put in liters, your answer would have been 0.02 liters. Knowing what you know now about lab equipment, isn't it a lot easier to say I'm going to measure out 20 mils than to measure out 0.02 liters, right? And that's pretty much how the dilution works. You're almost always going to want to use mils, but you wouldn't have been wrong had you given me an answer 0.02 liters. I wouldn't have marked you wrong. It would have been fine. So now we know how much of that solution we need, but what I need from you is to tell me how to make it. This is an example of, we want 250 mils of this. Here's a 250 mil volumetric flask. For those of you at home, it kind of looks like this. And it's got a little 250 written here, and it's got a line. So what are we going to do? Trevor? Okay, put what solution? We've got to be specific. Put 20 mils of what? We're making this from that, right? 20 mils of 0.5 molar copper 2 nitrate into what? $250 ml flask. Nope, you can't. The volumes aren't additive. I'm glad he said that. He said put it into 230 mils of water. You really can't do that. In this case, it wouldn't be too bad because that's not a super concentrated solution. But you can't assume that these things are additive because their densities are different. Okay. Again, you want to go to total solution. So we're going to put 20 mils into this 250 ml flask and do what? Add H2O until when? I overflow it to the 250 ml line. I know it seems like I'm stating the obvious, but yeah, I'm stating the obvious, and I want you to state the obvious. This is how you make it. Once we're done testing you on this, where I feel a little more secure with your abilities, you will be able to go back and do this, and I will expect you to do this in some labs, okay? Any questions? Last problem of the day, next. Determine the molarity of Cl- ions in a solution prepared by dissolving 9 point, so we want the molarity. Brackets mean molarity. And we're taking 9.82 grams of copper 2 chloride in enough water to make a 600 ml solution. Any ideas? This is not too hard of a problem. It's kind of the reverse of what we just did. So we want to find molarity. Just go back to what you know. What is molarity? Moles per liter. I already know one of them off the top. What? I'm looking for molarity. I already know I'm making 600 mils of solution, so I've got 0.6 liters. If I convert, yes, Winborn says convert grams to moles. If I convert these grams to moles, what am I getting the molarity of? That gives me the molarity of what? Of the whole thing, right? That's molarity of copper 2 chloride. But I need molarity of chloride. So I can do a couple things. Any ideas? We have the massive CuCl2. Okay, do we have to go all the way back to massive chlorine though? What do we, let me just look at this alone. If we want molarity of chloride ions, we need moles of chloride ions over the total volume, right? So all I need is moles of chloride ions right here. So I can do it I know there's two ways I can do this. I can find moles of copper 2 chloride and then find molarity of copper 2 chloride and then I can do something. Or I could go moles of copper 2 chloride and go to moles of chloride. You want to do that? Let's do that. Forget this for now and go to moles of Cl minus, and from there I can go to molarity of Cl minus. Is everyone okay with that? I'll show you the other way to do it in a sec, but let's just do this way first, because this to me makes most sense. It's the most direct way. So let's start with our stoic 9.82 grams of CuCl2. For every 1 mole, I have how many grams? 134.45 grams. Okay, so this is moles of CuCl2. But I need moles of the chloride ion. So for every 1 mole of CuCl2, I have 2 moles. Does that make sense? All right, so how many moles of chloride ions do I have? 0.146. I'm not done. This is moles of Cl minus, but I need molarity. So now I can plug all this stuff back into this guy. I need the molarity, and I have 0.146 moles of Cl minus divided by 0.6 liters, correct? Yeah. And then what's my molarity? 0.243 moles per liter of Cl minus. Another way you could have done it, and you'll get better at this the more experience you have with it, but you could have just found the concentration of CuCl2 moles per liter and then just multiply it by 2. How do I know that? When I look at that molecule, I say to myself, okay, if I have all of that dissolved, for every 1 of those, I have 2 of the chloride ions. So wouldn't that double the concentration of it? Wouldn't that double the moles per liter of it? So what you could have just done is solve for moles of CuCl2 and then say, oh, 2 chloride ions per that, so I'm just going to multiply it by 2. Either way would have been fine. It's the same way. It's the same thing. You would have just gone up here. The continuation of this would be then just multiply by 2, which mathematically is exactly the same thing that we did. Is everyone good? All right. No, I didn't ask how to make it. Yeah, that was a good question. Do we have to write out how to do it? No. The way I phrased this problem, no, I actually didn't phrase it very well the same. Here I wrote, how would you prepare? When I say how would you prepare, I want to know how would you prepare versus here it just says calculate. You'd only have to calculate. And I'm going to change that and how would you prepare? I'm just going to promise you right now you will be asked how to prepare a solution from a solid and from a dilution. Okay? That's I'm telling you right now. That's on it. Okay. That's it for the day. Good job.